In 1930, the concept of dark matter and dark energy was first introduced by Fritz Zwicky. The influence of these two sources of matter and energy on the formation of stars and galaxies has been supported by numerous observations and discoveries in modern cosmology. However, every cosmological model has its own shortcomings. The unique existence of an ancient galaxy completely devoid of dark matter is a significant blow to the astronomical community. It is challenging the efforts of scientists to answer the question, where does the origin and existence of the universe come from after billions of years? The presence of a dark matter-free galaxy raises many hypotheses about humanity's understanding of the vast 95% of the universe. Does this affect the process of sustaining the existence of the galaxy itself? And what does the future hold in store for us? Does dark matter truly exist, or is it just an excuse, a condition for the current limitations of humanity's knowledge? Let's explore the latest discoveries in this field to gain a deeper understanding of the vast universe and the significance of dark matter in maintaining the existence of magnificent galaxies. This is EYES 200M, and welcome back to join us on this journey. NGC 1277, the relic of the primordial universe. Dark matter and ancient galaxies. It's the enigma that has puzzled many scientists and astronomers of the 21st century. Discovering and observing these distant remnants is incredibly challenging due to the limitations of scientific technology. However, thanks to the presence of the James Webb Space Telescope, or JWST, humanity has been able to venture further in the search and exploration of the oldest relics in the universe, galaxies formed shortly after the Big Bang. Before the JWST embarked on its noble mission, NGC 1277 was just one of the faint red smudges in the southern sky as seen through the lens of the Hubble telescope. It was one of over 700 ancient galaxies captured by James Webb in early June. NGC 1277 is a dwarf elliptical galaxy located in the constellation of Andromeda. It is a member of the Perseus cluster and lies approximately 220 million light-years away from us. NGC 1277's apparent magnitude is around 14.7. It was discovered on December 4th, 1875, by Lawrence Parsons, the 4th Earl of Rosay. NGC 1277 is unique in that it is considered a relic of what galaxies were like in the early universe. The galaxy is composed exclusively of aging stars that were born 10 billion years or so ago. But, unlike other galaxies in the local universe, it has not undergone any further star formation. Astronomers nickname such galaxies as red and dead because the stars are aging and there aren't any successive generations of younger stars. The telltale sign of the galaxy's arrested development lies in the ancient globular clusters that swarm around it. The reddish clusters are the strongest evidence that the galaxy went out of the star-making business long ago. Otherwise, there would be a lot of blue globular star clusters, which are largely absent. The lack of blue clusters suggests that NGC 1277 never grew further by gobbling up surrounding galaxies. To be fair, our understanding of the grand relics of the universe, like NGC 1277, is far too limited. Before shocking the world with its meager dark matter content, NGC 1277 had perplexed many scientists with data concerning the supermassive black hole residing at its core. Recent findings indicate that the black hole at the center of the galaxy NG 1277 seems to account for about 59% of the total galaxy mass, the largest fraction of any supermassive black hole ever measured. It harbors a black hole with an approximate mass of 12 billion times that of our Sun. This far exceeds the expected mass of the central black hole in a galaxy of the modest dimensions of NGC 1277. We suggest that this giant black hole was ejected from the nearby giant galaxy NGC 1275 and subsequently captured by NGC 1277. The ejection was the result of gravitational radiation recoil when two large black holes merged following the merger of two giant ellipticals that helped to form NGC 1275. The black hole wandered into the cluster core until it was captured in a close encounter with NGC 1277. The migration of black holes in clusters may be a common occurrence. Most massive galaxies have supermassive black holes at their centers, and the masses of the black holes are believed to correlate with the properties of the host galaxy bulge component. Several explanations have been proposed for the existence of these locally established empirical relationships, including the non-causal statistical process of the galaxy merging, direct feedback between the black hole and its host galaxy, and the subsequent violent relaxation and dissipation. The empirical scaling relations are therefore important for distinguishing between various theoretical models of galaxy evolution, and they furthermore form the basis for all black hole mass measurements at large distances. Observations have shown that the mass of the black hole is typically 0.1% of the mass of the stellar bulge of the galaxy. Until now, the galaxy with the largest known fraction of its mass in its central black hole, 11%, was the small galaxy NGC 4486 B1-9. From observational experience, the existence of the central black hole in NGC 1277 remains a significant mystery. It is still unclear whether these galaxies represent the tail end of distribution, or if galaxies with dominant central black holes deviate from the typical mass black hole relationship seen elsewhere. When James Webb focused its observation on NGC 1277, scientists immediately recognized a significant issue from the images. The existence of a massive black hole led to parameters indicating that NGC 1277 is entirely devoid of dark matter. Is this a normal relationship in the universe, or are there still hidden secrets? Can black holes truly consume even the components known as dark matter? Or, fundamentally, does dark matter and dark energy not exist? If you are truly curious about what dark matter and dark energy have done to sustain the existence and formation of galaxies, I encourage you to check out the video James Webb Unveils the Mysterious Link Between Dark Energy and Black Holes in the Formation of Ancient Galaxy Clusters on our channel. The link will be provided right below the description for you. But for now, let's delve into the evidence from NGC 1277 to discover what is truly happening inside this ancient galaxy. I hope you'll keep an open mind, as what we are about to reveal may challenge some of your beliefs, what you've heard, and what you've learned so far. NGC 1277 has a severe dark matter deficiency. In the current standard model of the universe, dark matter and dark energy account for approximately 95% of the total mass in the universe, meaning only about 1/6 is composed of the ordinary matter that we interact with in our daily lives. Dark matter remains elusive. It does not interact like regular matter, and its existence is solely inferred from its gravitational effects on stars and gas in galaxies. According to the Lambda CDM cosmological model, present-day galaxies with stellar masses greater than 100 billion times that of the Sun likely contain a substantial amount of dark matter within their stellar bodies. Models indicate that in massive early-type galaxies, or ETGs, with masses around 115 billion times that of the Sun, dark matter must account for approximately 15% of the dynamic mass, within 1 effectual radius, or 1 RE, and about 60% within 5 REs. Most giant ETGs, or early-type galaxies, have been shaped through a two-phase process: a rapid formation of a compact core, followed by the accumulation of an extended outer envelope through mergers. Extremely rare galaxies have managed to avoid the second phase, known as relic galaxies, believed to be the frozen remnants of giant ETG populations at Z is greater or less than 2. The best-known candidate for a relic galaxy discovered so far is NGC 1277, located in the Perseus cluster. NGC 1277 is a relic galaxy, a galaxy that does not interact with neighboring galaxies. Relic galaxies are exceedingly rare and are considered vestiges of giant galaxies formed in the early universe. Scientists have utilized data from the George and Cynthia Mitchell spectrograph, or GCMS, Deep Field Integral Field Spectroscopy, to re-examine NGC 1277 at an unprecedented radius of 6 kpc, equivalent to 5 effective radiuses, or 5 REs. By employing a model called anisotropy genes modeling, they found that dark matter contributes insignificantly within the range of 5 REs, which contradicts the predictions of the Lambda CDM cosmological model. Cameron explained, "The significance of relic galaxies in helping us understand the formation of the early universe is the reason why we decided to observe NGC 1277 using integral field spectroscopy." From the spectra, we constructed dynamic maps that enabled us to understand the distribution of mass within the galaxy up to a distance of approximately 20,000 light-years. According to their findings, NGC 1277 contains no more than 5% of dark matter. Its mass distribution is solely determined by its stars. Current cosmological models predict that a galaxy of this size should have been between 10 to 70% dark matter. Dr. Ignacio Trujillo, a researcher at IAC and ULL, stated, "The discrepancy between the observations and what we expected is a puzzle, and it may even pose a challenge to the standard model." The research team proposed 2 possibilities to explain the lack of dark matter in NGC 1277. Dr. Anna Ferre-Matau, also from IAC and ULL, added, "One possibility is that gravitational interactions with the surrounding environment in the galaxy cluster containing this galaxy have stripped away the dark matter. The absence of an extended outer envelope reduces dynamical friction and prevents the accumulation of the outer layer. Therefore, Dr. Ferre-Matau suggests that NGC 1277 may have lost its dark matter very early on, or that it never had much dark matter to begin with. Scientists are currently discussing their discovery within the context of recent proposals, suggesting that some relic galaxies may result from dark matter being stripped away as they fall into and interact with galaxy clusters. Moreover, NGC 1277 could have been formed through a high-speed collision of gas-rich progenitor galaxy fragments, where dark matter left behind a dispersed baryonic disk. Standard calculations suggest that a relative velocity of about 2,000 kilometers per second or so is needed for the second process to occur, and this could plausibly take place in the ancestors of today's rich galaxy clusters. The issue remains that dark matter could have been expelled from the system during the galaxy's formation through the merging of progenitor galaxy fragments, resulting in a relic galaxy. However, both theories have left researchers unsatisfied. Cameron stated, "The puzzle of how a massive galaxy could form without dark matter remains an enigma. They plan to continue observations using the William Herschel telescope at the Roque de los Muchachos Observatory on the Canary island of La Palma. Perhaps surprisingly, the clear absence of dark matter in NGC 1277 is further evidence for its existence and raises significant doubts about alternative theories proposed to explain the observed effects in galaxies, such as theories suggesting a slight modification of the law of gravity on large scales. While dark matter may be missing in specific galaxies, a modified law of gravity must be universal. It cannot have exceptions. Therefore, a galaxy without dark matter would reject this alternative dark matter hypothesis. This presents a challenge to the Lambda CDM model itself. How many more secrets are hidden in the universe? Are we behaving like those who condemned Galilee? The truth is that the universe is too wide and contains too many questions. That's why I asked you to keep an open mind, because we will see many other great changes. The relationships between dark matter, dark energy, and ancient galaxies. Dark matter and dark energy are believed to have influenced the formation and evolution of galaxies during the early epochs following the Big Bang. Although they remain subjects of ongoing research and are not yet fully understood, hypotheses about dark matter and dark energy have been proposed to explain certain physical phenomena that cannot be accounted for by ordinary matter and energy. According to current physical models, dark matter is assumed to exert gravitational effects and play a crucial role in the formation of large structures in the universe, including galaxy clusters and cosmic filaments. Dark matter enhances the gravitational force in the universe, leading to the contraction and concentration of matter to form galaxies. Dark energy, on the other hand, is believed to have a repulsive effect on distant galaxies, contributing to the cosmic expansion between galaxies. Dark energy is a concept devised to explain the accelerating rate of expansion of the universe and why galaxies rotate around their axes at a certain speed without breaking apart due to centrifugal forces. According to this hypothesis, dark energy can provide an additional push, contributing to the formation of galaxy clusters and cosmic filaments. Dark energy enhances the gravitational force between objects in the universe, leading to the formation of large structures and uneven distribution of matter in space, resulting in the network of galaxies that we observe today. But how do we find them? Those entities that do not interact with regular particles and assert their role? Well, the answer lies in the past, with a fascinating journey that starts from the Coma Cluster. The Coma Cluster, also known as the Coma-Abell 1656 cluster, is one of the nearest and largest galaxy clusters that we know of. It lies in the constellation Coma Berenices and is approximately 320 million light-years away from Earth. It is also one of the richest galaxy clusters in the nearby universe. The Coma Cluster has an incredibly high galaxy density and contains many massive galaxies. On average, each volume of space within the cluster hosts about 10 to 15 galaxies. This means that in each smaller volume of the cluster, there exists a large number of galaxies clustered closely together. Well, what does this mean? According to the gravitational theory in physics, large galaxies within the Coma Cluster could move and merge within smaller galaxies at high speeds. However, galaxies within the cluster maintain stable velocities, and close galaxies can still avoid collisions and mergers. This contradicted previous calculations by space physicists. Hence, the concept of dark energy and dark matter emerged. According to the theory, dark matter interacts with regular matter through gravitational force. The presence of the matter in the Coma Cluster has caused galaxies to move slower than what was predicted by the gravitational force of regular matter alone. In the research paper strong and weak lensing united. The mass distribution of the merging galaxy cluster 1 IES 0657-558 derived from joint X-ray and lensing analysis. Scientists use strong and weak lensing measurements to determine the mass distribution within the coma cluster. The research findings revealed the existence of dark matter in the cluster and its significant impact. As a result, we were able to ascertain the presence of a substantial amount of dark matter, estimated to make up around 90% of the mass of coma. So, dark matter acts as a counterbalance, like a scale on the other side, to be in equilibrium with gravitational force. Put simply, if we were to remove dark matter, we would witness billions of galaxies colliding with each other every day. They would stop rotating around their axes and rush away from each other every second. Earth would also rush straight towards the Sun and become a part of it. This equilibrium has been maintained for billions of years since the birth of the universe. Evidence of this balance still exists in the images captured by the James Webb Space Telescope. There is only one reason to explain the current situation, and that is that we made a mistake right from the step of determining the types of particles and energy that make up the galaxies. We have been wrong from the very beginning of our theories. Scenarios of ancient galaxy formation. According to previous cosmological models, galaxies would continuously evolve and form new stars. However, without dark matter, the sources of energy to form new stars would be limited. As a result, galaxies would lack younger star generations, and the existing stars would continue to age without any replenishment. Early proposed scenarios for the formation of large primordial galaxies indicated a monolithic collapse similar to what was suggested for the oldest stellar populations in the Milky Way. However, these models have become outdated with the emergence of cold dark matter formation models in cosmology. Recent computational studies based on the Lambda CDM cosmological framework, however, suggest that nature borrows from both scenarios, and the process of forming massive ETGs, again, early-type galaxies, can be divided into two stages. Initially, the giant ancestors of ETGs undergo a dissipation-less collapse, resulting in a compact rotating object where star formation is quickly suppressed, possibly due to the activity of an active galactic nucleus, or AGN. In the second stage, the massive evolution of the stellar population transforms the blue-hued objects into red, and most of the stellar mass growth of the object comes from the accumulation of an extended outer shell supported by pressure through dry accretion. The account of this simplified two-phase formation is supported by observations indicating that galaxies evolve passively at higher redshifts, being much more compact than local massive ETGs, and they have grown 4 times in effective radius since redshift, or z is infinity more than 2. This framework is supported by the fact that stellar shells have been demonstrated to develop over cosmic time. Additionally, recent identifications of small, compact, star-forming and likely rotating super-red nuggets might provide further evidence for the two-phase formation scenario. Detailed studies of NGC 1277 have provided a unique and profound insight into the harsh conditions where nuggets develop. Martín Navarro and colleagues discovered that the initial mass function, or IMF, of NGC 1277 is the heaviest across all galaxies, implying a high mass-to-light ratio of stars. Similarly, slightly less extreme properties have been confirmed for 2 other relic galaxies. Furthermore, dynamical modeling revealed that almost no dark matter is needed to explain the dynamics of stars within the innermost 13 inches of NGC 1277. Conclusion. Thus, the relationship and correlation between dark matter and galaxies remains a mysterious puzzle that requires further exploration. The discoveries about NGC 1277 have provided valuable insights into the formation and evolution of relic galaxies. The evidence and models have revealed surprising and intriguing aspects concerning the dynamics, central black holes, and the development of dark matter in the universe. If you are still curious and eager to explore more about the latest discoveries in this field, stay tuned for our James Webb video about the enigmatic connection between dark energy and black holes in the formation of ancient galaxy clusters. In the meantime, we sincerely thank you for joining us today on this journey. Keep following and discovering the fascinating and novel aspects of the universe in the future. See you in upcoming videos. Thank you and have a wonderful day.